AI agents are, well, they're just exploding into our lives, aren't they? From automating tasks at work to helping us navigate our digital world. And the investment pouring into this space is absolutely staggering. For a long time, the widely held belief has been that large language models, LLMs, are the foundational brains behind it all. But what if that deeply ingrained assumption is, well, maybe not the whole picture? We've got this fascinating new paper from NVIDIA Research that throws a pretty significant wrench into that idea.
Yeah, it really does. And our mission today on the deep dive is to unpack exactly why this paper argues that small language models, or SLMs, are the future of agentic AI. We're going to examine their core arguments, look at some potential counterpoints, and even explore a practical roadmap for how this shift might happen. And just so we're clear, when we say SLM, we're talking about models small enough to run on, say, your phone or laptop, giving low latency responses for one person. An LLM is basically anything bigger than that, often models with over 10 billion parameters.
Right. And crucially, this isn't just about some minor technical tweak in the background. This is about a fundamental shift. It could have, well, enormous economic and operational impacts for you, whether you're just interacting with these agents daily or maybe even thinking about building them yourself. So let's start with where we are right now. AI agents, I mean, they've truly had this meteoric rise. We're seeing surveys showing over half of large IT enterprises are already using them, with a really significant chunk adopting them just in the last year. The market clearly sees huge value here. There's been, over $2 billion in startup funding recently, and the sector's current valuation, around $5.2 billion, is expected to just skyrocket to nearly $200 billion by 2034. It's incredible growth.
It really is. And for
Yeah.
most of these modern AI agents, the LLM is the core component, yeah?
Yeah.
It's the brain orchestrating everything. These big model and help agents make strategic decisions, use tools effectively, break down really complex tasks, plan out actions, and typically agents access these LLMs through centralized cloud API endpoints. That's the standard model. This model is so deeply ingrained, it's the foundation for these massive capital bets. You mentioned the market size for LLM API serving around 5.6 billion in 2024.
Yeah.
Well, the investment into the hosting cloud infrastructure for these models, that surged to an astonishing $57 billion in the same year. $57 billion.
Wow. So all that investment, all that scale focused on LLMs,
Mhm.
you'd naturally think that's the only way forward, right?
Yeah.
But this is where that NVIDIA paper really grabbed my attention. They argue maybe we've been looking in the wrong place, or at least not considering all the options. They do directly challenge this idea that these powerful generalist LLMs are always the best fit for agents. It sounds like they're suggesting a pretty fundamental reevaluation of what makes an agent truly smart and efficient.
Exactly. The paper's core argument is clear and, yeah, quite provocative. SLMs are the future because they are, one, principally powerful enough, two, inherently more operationally suitable, and three, necessarily more economical for the vast majority of agentic uses. And they don't just say it's a good idea, they present it as a kind of necessary consequence of how agents actually operate day to day.
Okay, you mentioned this necessary consequence. Can you elaborate on why agent tasks are so fundamentally different that an LLM might actually be overkill? Maybe give us an everyday kind of example.
Absolutely. Think about most tasks an AI agent performs. They're
Yeah.
actually quite repetitive, right? They're narrowly scoped, and often they aren't even conversational in the way we think about chatbots. Imagine an agent helping you book a meeting. It doesn't need to write a novel or, get into a deep philosophical discussion.
Mm.
It needs to understand specific commands, find a time next Tuesday, interact with particular tools, precisely like your calendar API, and just get the job done. A generalist LLM, which is designed for this really open-ended conversation and broad knowledge, is often, frankly, overkill for these discrete, well-defined tasks.
So it's like using a supercomputer to run a calculator, essentially.
That's a great analogy, yeah. And this leads into the concept they discuss: heterogeneous agentic systems. The idea is basically to use SLMs by default for most of these routine tasks and only bring in the much larger, more expensive LLMs selectively. Maybe for things like really complex reasoning steps or genuinely open domain dialogue parts. This kind of modular composition, mixing and matching, creates systems that are both highly cost-effective and perfectly capable. It aligns the model with the specific demands of each subtask.
Using the right tool for the right job, scaled appropriately. Makes sense.
Exactly.
But I think the big question for many listening will be, can these smaller models really do the heavy lifting? Can they handle the complexity? Let's dig into the latest evidence that suggests, well, yeah, maybe they absolutely can.
Yeah, and this is where things get really interesting. SLMs have advanced dramatically. While, scaling laws still apply, bigger models generally do get better, the curve relating model size to capabilities is getting much, much steeper. What that means is that newer, more efficient SLMs are increasingly able to perform like much larger, older LLMs. They're rapidly closing that performance gap.
And we're not just talking theory here, right? There are concrete examples coming out now.
Oh, definitely. Take Microsoft's Phi 2 model. It's just 2.7 billion parameters, tiny compared to the giants, but it can actually match 30 billion parameter models in areas like common sense reasoning and even code generation. And it's about 15 times faster.
15 times faster. Wow.
Or look at Salesforce's XLM28B. That's an 8 billion parameter model. It's achieving state-of-the-art results in tool calling, basically, getting the AI to use external software tools correctly. It's surpassing even giants like GPT-4o and Claude 3.5 in some benchmarks.
That's impressive for an 8B model.
And it's a consistent pattern. You look at Hugging Face's Small N2, NVIDIA's own Nemotron H family. These smalling models, often just a few billion parameters, are now demonstrably matching or even outperforming much larger, sometimes much older, LLMs on critical agentic tasks like code generation, instruction following, and tool use.
It really feels like a clear signal that less can be more if it's designed right.
Precisely. And it doesn't even stop at the base model capabilities.
Right.
SLM performance can be boosted at inference time. That's when the model is actually running and generating output. You can use techniques like self-consistency, where it checks its own work, or verifier feedback, or tool augmentation. For instance, there was a model called Toolformer, only 6.7 billion parameters. It actually outperformed the original GPT-3, which was 175 billion parameters, simply by being really good at using external tools as part of its process.
Okay, so the takeaway here for you, the listener, seems pretty fundamental. When we think about AI capability for a lot of what agents do, it's maybe no longer just about the raw parameter count or that brute force size. It's becoming more about smart design, targeted training, and delivering that performance in a much, much more efficient package.
Exactly. And that efficiency translates directly and dramatically into economic impact. Serving a 7 billion parameter SLM is, get this, 10 to 30 times cheaper than serving a 70 to 175 billion parameter LLM. That's across latency, energy consumption, and computational needs.
10 to 30 times cheaper. That's
Yep.
just a staggering difference, especially when you think about real-time responses for users or deploying these agents at massive scale. And I imagine that impacts the underlying infrastructure needed too, right? Does it mean fewer complex systems?
Absolutely. SLMs often require less or sometimes, parallelization across multiple GPUs. You don't need these huge complex clusters as often. That translates directly to lower maintenance and operational expenses. It's just simpler to run.
Okay.
And another huge advantage they highlight is fine-tuning agility. Adapting an SLM for a new task or updated requirement can take just a few GPU hours.
GPU hours, right? That's the compute time measure.
Yeah, so you can potentially get updates or specializations done overnight. Compare that to weeks, sometimes longer, for retraining or heavily fine-tuning a massive LLM. Plus, SLMs really enable edge deployment. That means you can run them directly on consumer-grade devices, your phone, your laptop.
Right on the device itself.
Exactly, which allows for real-time offline use cases and significantly improves data control and user privacy because the data doesn't have to leave the device.
It really is like building with Legos, isn't it? This
Yeah.
Lego-like approach, adding small specialized models instead of trying to scale one huge monolithic thing. It makes the whole system inherently cheaper, faster to debug if something goes wrong, and just much easier to deploy and update as your needs change. It really promotes a modular design.
It does, and that modularity ties into flexibility. Because they're smaller and cheaper to run and train, it becomes practical to have multiple specialized expert SLMs, each tuned for different specific agentic routines or tasks. This dramatically increases the operational flexibility compared to relying on one giant do-everything LLM.
And that flexibility must be huge when you think about, say, rapid iteration, adapting quickly to evolving user needs, or maybe new behaviors you wanted the agent to learn, or even changing local regulations or compliance rules. You can tweak the specific module.
Precisely. It allows for much greater agility in development and deployment. And crucially, this flexibility, this lower barrier to entry, also potentially leads to what the paper calls the democratization of AI agents. When more individuals, more smaller organizations can actually participate in developing and deploying these models, it fosters a more diverse range of perspectives and innovation. It broadens who gets to build with and benefit from AI, potentially reducing systemic biases too.
It's a really important point. Now, one of the paper's arguments that I found really compelling was about how agents already work. They essentially restrict these incredibly powerful generalist LLMs down to a small set of skills anyway, usually using carefully written prompts, right? It almost feels like you're hiring a super genius to do relatively simple, repetitive tasks.
That's a perfect analogy. An SLM, if it's appropriately fine-tuned for that specific task, can perform those narrow functions just as well, maybe even better because it's specialized. And you get all the efficiency and flexibility benefits we've been discussing. You're actually giving the right, properly sized tool for the job rather than this vastly overqualified one.
Yeah, makes sense. And speaking of specific tasks, agent-to-code interactions, like calling an API or parsing data, they demand really strict formatting, don't they? Like using JSON or XML correctly. Precision is absolutely critical there.
It is critical. A single misplaced comma can break the whole process. And SLMs can be specifically trained, fine-tuned to consistently conform to these required formats. This helps reduce those hallucinatory mistakes you sometimes see with generalist LLMs where they might drift off script or generate improperly formatted output. And doing that specialized format training is far more practical and cost-effective with SLMs because the training process itself is so much cheaper and faster.
What's also fascinating, you touched on this earlier, is that agentic systems seem almost naturally set up for this kind of heterogeneity already. The way they work, one language model can actually call another language model as if it were a tool. Or the agent's core code can simply choose which model to use based on the specific task at hand. I think you mentioned figure 1 in the paper illustrates this. It seems like they were almost designed for this modularity from the start.
Exactly. The architecture allows for it inherently. You could have an LLM acting as the main orchestrator, maybe guiding the overall goal or handling a complex part of the dialogue, but then it could delegate a subordinate task like extracting specific information or formatting output to a specialized SLM. This multi-model approach naturally accommodates SLMs. It allows for this mix and match strategy where the right model, scaled appropriately, is used for exactly the right part of the job.
Okay, and there's one more argument they make that links SLMs to continuous improvement involving data. Tell us about that.
Right. So every interaction an agent has, every time it calls a tool, every time it invokes a language model, every response it gets that's potentially a source of incredibly valuable training data.
Oh, so you log those interactions.
Exactly. Logging this data, specifically the inputs and successful outputs for these narrow tasks, can help produce high-quality, specialized instruction data sets over time. This data can then be used to further fine-tune an expert SLM, leading to continuous improvement in its performance on that specific task, and potentially even lower costs in the future as the model gets better and more efficient.
So it's like the agent is continuously training its own specialized, cost-efficient brain, constantly improving its specific skills based on real-world use. Creates a powerful feedback loop.
It creates a very powerful virtuous cycle, yes.
Okay, this vision sounds incredibly compelling. More efficient, cheaper, more flexible, even potentially more democratic AI agents. But of course, any major proposed shift like this is going to have its skeptics. What are some of the main doubts or counterarguments people raise, and how does the paper address them?
Well, probably the most common belief, the one really prevalent in academic circles and the popular press, is that LLMs, simply because they're larger, will always outperform SLMs on any language task, no matter how narrow it seems. This is often attributed to their superior general language understanding, their broader world knowledge, and something researchers sometimes call a semantic hub.
A semantic hub.
Yeah, the idea is that these huge models develop a kind of central representation that allows them to integrate and abstract meaning across different types of information, different modalities, different languages, in a way smaller models supposedly can't.
Okay, that makes intuitive sense on the surface. Bigger brain, better understanding overall. So what are the paper's specific rebuttals to this idea that bigger is always better, especially regarding this semantic hub concept for agent tasks?
The NVIDIA paper offers some strong rebuttals. First, they point out that scaling laws, the study showing bigger is better, often assume a constant model architecture. But SLMs are increasingly being developed with different optimized architectures. Things like hybrid Mamba transformer models, which might offer unique performance benefits specifically at smaller scales. So it's not always an apples-to-apples comparison.
Okay, so the architecture itself matters, not just the size.
Right. Second, they emphasize the flexibility of SLMs for fine-tuning. They can be very easily and cheaply adapted to excel at specific tasks, and this task-specific tuning isn't always accounted for in those general scaling studies that just measure broad benchmark performance. And regarding this semantic hub idea, the paper argues, look, this broad abstract understanding is probably most useful when the tasks or the inputs themselves are inherently complex and ambiguous. But, as we discussed earlier, advanced agentic systems are often designed precisely to break down complex problems into simpler, more manageable subtasks. So when you're calling a model for a very specific, well-defined piece of a larger problem, that super general understanding from a semantic hub might actually be far less critical for that specific invocation. You need precision more than breadth at that point.
That makes sense. You don't need the model to understand the entire universe just to format a date correctly.
Exactly. Another counterargument focuses more on economics. Some argue that, okay, while SLMs might be cheaper per token or per inference call, the overall economy of scale for these huge centralized LLM providers might still win out in the end. They point to the potential difficulty of achieving high utilization, like keeping the servers busy, for lots of small, specialized SLM endpoints compared to one massive LLM serving everyone. And they also mention the potentially high costs of setting up and maintaining the necessary infrastructure and specialized talent for managing lots of different SLMs. It's kind of it's already built, the ecosystem is there, why change argument.
Right, the operational overhead of managing many small models versus one big one.
Yeah. And the paper acknowledges this as a valid point where perhaps the jury is still out to some extent on the overall system economics. However, it also points to recent and ongoing improvements in inference scheduling technologies, basically, the software that efficiently manages incoming requests and assigns them to the right AI models. Things like NVIDIA's own Dynamo system are making it much easier and more efficient to manage diverse SLM workloads, even within monolithic computing clusters. This allows for much better utilization. They also note a consistent falling trend in the costs associated with setting up infrastructure, driven by underlying technological improvements, so that barrier might be shrinking.
Okay, so technology might be catching up to make managing SLMs more feasible at scale. What about just inertia? The idea that even if SLMs are objectively better in many ways, the LLM-centric world just has such a significant head start. There's this massive industry, inertia funding, tooling, mind share, all pushing towards bigger LLMs, making a fundamental shift really difficult.
Yeah, that's definitely a real factor. The paper acknowledges this inertia as a distinct possibility, a major hurdle. But it ultimately maintains that the collective advantages of SLMs, there's sufficient power for many tasks, their superior economics, their operational flexibility are just so compelling that they are plausible, maybe even likely, to overturn the status quo over time. The economic incentives in particular might just become too strong for businesses to ignore indefinitely.
Okay, so if the arguments for SLMs are so strong and the counter-arguments have reasonable rebuttals, you might be asking yourself, why aren't SLMs more widely adopted right now? Why do the newer generations of agents we see still seem to mostly rely on these big centralized LLMs? What are the roadblocks?
It's a great question, and the paper identifies some key practical hurdles. Importantly, they frame these not as fundamental flaws of SLM technology itself, but more as ecosystem or historical factors. The first major one is the sheer scale of the upfront investment that has already been poured into centralized LLM infrastructure. We talked about that $57 billion figure earlier.
Right.
This massive capital bet has naturally led to tools, platforms, and standard practices being built primarily for LLMs, perhaps inadvertently overlooking or deprioritizing decentralized or on-device SLM possibilities. The path of least resistance leads to the existing infrastructure.
So the existing investments create a kind of lock-in effect.
To some extent, yes. A second barrier they point to is the historical focus on generalist benchmarks in SLM training, design, and even evaluation. A lot of the academic and industry effort has been focused on making SLMs perform well on the same broad benchmarks used for LLMs, like language understanding tests or coding challenges in general. The focus hasn't always been on specifically measuring their utility for agentic tasks like tool use accuracy or format adherence or task completion rates in an agent workflow.
So we might have been measuring them against the wrong yardstick for this specific use case.
Potentially. And interestingly, the paper notes that when the evaluation focus is shifted specifically to agentic utility, SLMs often do outperform larger models in those specific narrow contexts.
Okay, that's interesting. And the third barrier?
The third is simply a lack of popular awareness and maybe marketing focus. SLMs just don't get the same level of hype, the same intensity of press attention as the latest giant LLMs do. This is despite their, as the paper argues, undeniable suitability and advantages for many common industrial and enterprise scenarios involving agents. They're just not as visible.
Right. So summing those up, it sounds like the barriers are mainly Existing infrastructure investment, favoring LLMs, maybe focusing on the wrong performance metrics, and just less general awareness or buzz around SLMs. It's important to reinforce, as you said, that these seem like practical, maybe temporary hurdles, not fundamental flaws in the SLM approach itself.
Exactly. And as the economic and operational benefits become clearer and more widely understood, these barriers are likely to diminish. For instance, those advanced inference scheduling systems like Dynamo we mentioned, they are already reducing the impact of that upfront investment barrier, making it easier to integrate SLMs into existing setups. It feels like the technology is increasingly ready, but the broader ecosystem and mindset perhaps need time to catch up.
So for organizations or developers listening who are intrigued by this, who might be thinking about making this shift, does the paper offer any practical guidance? Like, how would you actually go about migrating an agentic application from using an LLM to using SLM?
Yes, it does. It outlines a pretty clear step-by-step algorithm for making this transition, making it quite actionable. The very first step is secure usage data collection. This is crucial. It means systematically logging all the non-human interaction calls your agent makes to the language model. You log the prompts it sends, the responses it gets, any tool calls involved, the latency. But critically, you must do this while ensuring user privacy and data anonymity are strictly maintained.
Okay, so basically install a detailed but privacy-preserving logger on the agent's communication with its current LLM brain. Figure 1 in the paper probably helps visualize this.
Precisely. Step 2 is data curation and filtering. Once you've collected a sufficient amount of this logged data, the paper suggests 10,000 to 100,000 examples is often enough for fine-tuning SLMs. You need to carefully curate it. This involves cleaning the data and rigorously removing any potentially sensitive information, like personally identifiable information, PII, to ensure data security before you use it for training.
Got it. Collect the data, then clean it thoroughly. What's next?
Step 3 is task clustering. You then use AI techniques, maybe even another language model, to analyze the collected prompts and responses and identify recurring patterns or distinct types of tasks the agent is performing. For example, you might find clusters related to intent recognition or extracting specific data fields or generating code snippets or summarizing text. These identified clusters essentially define the specific specialized SLMs you'll need to create or fine-tune.
So you figure out the distinct jobs the agent is actually doing. Makes sense.
Step 4 is SLM selection. Based on those identified task clusters, you then choose the best candidate SLMs for each job. You'd consider their inherent capabilities based on general benchmarks, maybe look at benchmarks specific to that task type if available, and importantly, consider their deployment requirements, size, speed, cost.
Right. Pick the right small tool for each specific job you identified.
Exactly. Step 5 is where the magic happens. Specialized SLM fine-tuning. You take the chosen SLMs and train them specifically on the curated datasets corresponding to each task cluster. And you typically use highly efficient fine-tuning techniques like LoRa or QLoRa. These are methods that update only a very small fraction of the model's parameters, making the tuning process incredibly fast and cheap compared to retraining the whole model.
Okay, so you're not training from scratch, just adapting existing SLMs very efficiently.
Often, yes. Or you could even use a technique called knowledge distillation, where the small SLM learns by trying to mimic the outputs generated by the original, larger LLM on that same task data. It learns from the master, so to speak.
Interesting. And the final step.
The final step is iteration and refinement. This isn't a one-time process. You should ideally continue to collect new interaction data, periodically rerun the clustering and fine-tuning steps, and update your specialized SLMs. This keeps their performance high, allows them to adapt to evolving user needs or new patterns, and creates that virtuous cycle of continuous improvement we talked about earlier. Your agent system gets progressively better and potentially even more cost-efficient over time.
That roadmap really provides a concrete path, doesn't it? It takes it from an interesting theoretical idea to something organizations can actually start implementing to leverage SLMs, making their agent systems potentially much more efficient and sustainable. It's a clear game plan.
It really is. It demystifies the process.
So as we wrap up this deep dive, what really stands out to you, you've explored this really powerful argument from NVIDIA research suggesting that small language models, not just their giant counterparts, are potentially poised to fundamentally transform agentic AI.
Yeah, for me, if we connect this to the bigger picture, the shift to SLMs isn't just about saving money or making AI faster, though those are huge drivers. It's also about building more sustainable AI infrastructure. Think lower energy consumption, and critically, about democratizing access to this transformative technology. It potentially allows a much wider range of individuals and organizations to build, deploy, and innovate with AI agents.
That's a great point. And it raises a really important question for you, the listener, to maybe ponder after this. As AI agents become more and more prevalent in our daily lives, how might a future potentially dominated by these specialized, efficient, maybe even locally run SLMs instead of just monolithic cloud-based LLMs, how might that change the very nature of human AI interaction? And what could it mean for the pace and direction of innovation itself?
It's a fascinating question, and it's worth noting the authors of the paper explicitly call for further contributions and critique of their position. They're inviting a broader discussion within the community on the effective, efficient, and responsible use of our growing AI resources. It feels like the conversation is really just beginning.